All right, buckle up, AI enthusiasts. Ever wondered how safe those large language models actually are? Or how AI can truly see and understand the world like we do? We're diving deep into the heart of AI safety, vision, and reasoning today. It's going to be a wild ride.
Exactly. Today we're unpacking some cutting-edge research. First, we'll explore the full life cycle of LLM safety, from the data they're trained on to how they're deployed. Think of it as full-stack safety, covering every angle to keep these powerful tools in check. Then we're bridging the gap between vision and language, showing you how AI can learn to generalize what it sees to new situations. After that, we'll look at how to create better training data for these models so they don't hallucinate or make things up. Finally, we'll tackle the tricky topic of aligning AI with human values across different cultures and teaching AI to reason about geometry. It's a packed agenda, so let's jump right in.
All right, let's dive into this paper. A comprehensive survey in LL Agent full stack safety, data, training, and deployment. It's a mouthful, but it seems like they're trying to cover all the bases when it comes to making sure these things don't go rogue.
Exactly. It's not just about stopping the obvious bad stuff, but looking at the entire life cycle of an LLM. They're calling it full-stack safety, which I think is a good way to put it. Data, training, deployment, the whole shebang.
So what's new here? I mean, we've seen surveys on LLM safety before, right?
Yeah, but those usually focus on one specific area, like deployment or fine-tuning. This one claims to be the first to look at the entire life cycle. They've reviewed over 800 papers, which is pretty intense, and they're trying to create a roadmap for safety at each stage.
800 papers. Okay, they're serious. What are the key stages they've identified?
They break it down into data preparation, pre-training, post-training, deployment, and commercialization. Post-training gets further divided into alignment and fine-tuning, plus model editing and unlearning.
Model editing and unlearning. That's interesting. So not just training it right from the start, but also fixing it later on?
Precisely. Model editing is like surgical adjustments to the model's knowledge, and unlearning is about removing specific information. Think of it as the undo button for AI.
Okay, let's start with data. What are the safety concerns there?
The big ones are data poisoning and privacy leakage. LLMs need tons of data, and a lot of it comes from the internet, which is full of toxic stuff and personal information. That stuff can get baked into the model itself.
Data poisoning. That's when someone deliberately injects bad data to mess with the model, right?
Exactly. Even a tiny bit of poisoned data like 0.1% can have a lasting impact, and it's hard to detect because these attacks are often designed to be subtle.
And privacy leakage. That's the model accidentally spitting out someone's personal info?
Yep. LLMs can memorize and reproduce sensitive information from their training data. Data extraction attacks are designed to pull out that info. There are also membership inference attacks, which try to figure out if a specific piece of data was used in training the model.
So what can we do about all this bad data?
That's where data filtering comes in. They talk about heuristic-based filtering, which uses block lists and keyword matching to remove undesirable content. Then there's model-based filtering, which uses AI to assess the content. And finally, black box filtering, which relies on policy-driven or API-based methods.
What about data augmentation? I thought that was about making the model better, not safer.
It can be both. In this context, it's about adding safe demonstration examples to guide the model's behavior and annotating toxic content to help the model recognize and handle unsafe inputs.
Okay, so we've cleaned up the data as much as possible. What about the pre-training phase?
Well, even with filtering, some bad stuff can still slip through. The pre-training process is unsupervised, so the model can unconsciously absorb toxic data and privacy information. It's like its genetic makeup gets tainted.
That sounds pretty scary. So what happens if the model isn't properly aligned with security measures before deployment?
That's where post-training comes in. If it's not properly aligned, it can easily deviate from human values. And then there's fine-tuning, which uses safer, more customized data to make the model perform well in specific areas.
What about jailbreak attacks? I've heard those are a big problem.
Absolutely. That's a major concern during deployment. And it's even worse for LLM-based agents because they interact with tools, memory, and the environment, which can all be contaminated.
So how do we defend against these attacks?
They categorize defensive mechanisms into 3 groups: alignment, downstream fine-tuning, and safety recovery. Alignment is about making sure the model aligns with human values. Downstream fine-tuning is about creating robust fine-tuning mechanisms to defend against attacks. And safety recovery is about fixing the model after it's been attacked.
And what about model editing and unlearning? How do they fit into all this?
They're like lightweight adjustments that can be made during deployment to enhance security and privacy. Model editing addresses knowledge conflicts, while unlearning is about erasing knowledge to protect privacy.
So it's like constantly tweaking and refining the model to keep it safe and aligned?
Exactly, it's an ongoing process, not a one-time fix.
What about multi-agent systems? Do they have their own unique safety challenges?
Definitely. In multi-agent systems, you have to worry about the propagation of harmful information, hallucinations, and biases through agent interactions. You also have to worry about coordinated attacks targeting security agents within the system.
That sounds incredibly complex. So, what's the bottom line? What are the key takeaways from this survey?
The big picture is that LLM safety is a full-stack problem. You can't just focus on one area. You have to look at the entire lifecycle. Data generation is crucial. Post-training phases are becoming increasingly important, and model editing and unlearning are essential for efficient model updates. And finally, LLM agents require robust safety assurances.
So it's a never-ending arms race between the good guys and the bad guys, constantly trying to outsmart each other?
Pretty much. But hopefully with more research and a full-stack approach to safety, we can stay one step ahead and make sure these powerful tools are used for good.
All right, let's dive into this paper on domain generalization using vision and language integration. The core problem they're tackling is how to train a model on one set of data, the source domain, so it can accurately perform on a completely different, unseen set of data, the target domain. Think training a model to recognize cats using only photos and then expecting it to work on sketches of cats.
That makes sense. It's like teaching a robot to navigate indoors and expecting it to immediately handle outdoor environments. So what's their approach to bridge this domain gap?
Exactly. They propose something called VLCA, which stands for Vision Language Connection Alignment. The key idea is to leverage both the semantic richness of language and the intuitive nature of images. They use language as a bridge to connect different image domains.
Interesting. So how do they actually combine vision and language? It sounds like they're trying to find some common ground between the two.
Precisely. In the language space, they use word vectors to capture the semantic relationships between different categories. Word vectors, by the way, are numerical representations of words, where words with similar meanings are located closer to each other in a multi-dimensional space. Then, in the vision space, they use something called low-rank approximation to find common patterns in image features within the same category.
Okay, slow down a bit. What's low-rank approximation? It sounds a bit technical.
No problem. Imagine you have a matrix filled with image features. Low-rank approximation is a way to simplify that matrix by finding its most important components. It's like summarizing the key features that define a category, ignoring the noise or less important details. This helps to identify common patterns among images of the same class, even if they come from different domains.
Got it. So, they're using word vectors to understand the relationships between categories and low-rank approximation to find common visual patterns within each category. How do they bring these two together?
That's where the multimodal space comes in. They align the language representation with the vision representation using a multimodal space of text and images. This alignment is achieved by constraining domain-specific information, making domain embedding and image features orthogonal.
Orthogonal in this context?
Think of it as making them independent. They want to ensure that the image features don't contain domain-specific information that could hurt the model's ability to generalize. By making the domain embedding orthogonal to the image features, they're essentially removing the domain-specific style from the image, leaving only the core semantic information.
That's a clever way to decouple the content from the style. The paper mentions something about domain information orthogonal decoupling module. What's that about?
That's one of the 3 main modules in their approach. It uses CLIP, contrastive language image pre-training, to construct domain embeddings. CLIP is a model that's trained to understand the relationship between images and text. They use CLIP to create embeddings that represent the style of each domain, and then they force these embeddings to be orthogonal to the image features.
And the other 2 modules?
The second module is the word vector interclass constraint module. This uses word vectors to supervise the relationships between different categories. It encourages the model to learn that, for example, a dog is more similar to a wolf than it is to a car. The third module is the intraclass feature consistency module, which uses low-rank decomposition to find common patterns among samples of the same category.
So it's like a 3-pronged approach. Remove domain-specific information, enforce semantic relationships between categories, and ensure consistency within each category. Makes sense. Did they test this VLCA method?
Absolutely. They evaluated it on several domain generalization benchmarks like PAX, Office Home, VLCS, and Terrain Cognita. The results show that VLCA performs quite well, often achieving optimal or near-optimal results compared to other methods.
Any specific data sets where it particularly shines?
They found it worked especially well on datasets with rich textures and details like the photo and art domains in PAX. The semantic information also helped with more abstract domains like cartoon and sketch.
What about limitations? Every method has its weaknesses.
Good point. They acknowledge that the domain information decoupling relies on meaningful semantic prompts for CLIP. If the domain information is unclear, the effect is reduced. Also, the word vector constraint is limited by the completeness of the word vector model. If a category word isn't in the model, they have to use substitutes, which might not be ideal. Finally, the low-rank decomposition is affected by the batch size. Larger batch sizes generally lead to better results.
So it sounds like this VLCA method is a promising approach to domain generalization, but it's not a silver bullet. It relies on the quality of the language models and the clarity of the domain information. Still, the idea of combining vision and language to bridge the domain gap is pretty innovative.
Exactly. And they suggest that as language models continue to improve, and as we find better ways to represent images with semantic properties, the performance of methods like VLCA will only get better. So this paper is all about creating better synthetic captions for training vision language models, or VLMs. It's called Low Hallucination Synthetic Captions for Large-Scale Vision Language Model Pre-Training.
Okay, so why synthetic captions? What's wrong with the real ones?
Great question. The problem is that high-quality image-text pairs are getting scarce. Most VLMs are trained on web scrape data, like alt text from images, but that data is often noisy, incomplete, or just plain wrong. As models get bigger, we need more data, and the quality of web scrape data drops off a cliff.
Ah, so it's a quantity versus quality issue. Makes sense. So, they're trying to generate captions that are both high quality and plentiful.
Exactly. And the big challenge is hallucinations. That's when the caption says something that isn't actually in the image. The paper introduces a pipeline to generate captions that are low on hallucinations and rich in knowledge.
Hallucinations. Got it. Like a cat riding a unicorn when there's just a cat in the picture. How do they tackle that?
They use a method called direct preference optimization, or DPO. Think of it as a way to train the model to prefer captions that stick to the visual facts and avoid making stuff up. They're essentially increasing the model's confidence in what it actually sees and suppressing the urge to hallucinate.
DPO. Interesting. So it's like giving the model a reward for being accurate? How effective is it?
Pretty effective. They saw a significant jump in the non-hallucination rate. For a 7B size model, it went from about 48% to almost 78% on their test set. That's a huge improvement.
Wow, that's impressive. So DPO helps with accuracy. What about making the captions more informative?
That's where knowledge-enriching SFT comes in. SFT stands for supervised fine-tuning. They're basically injecting as much knowledge as possible into the captions. They use a powerful VLM GPT-4o with carefully crafted prompts to extract key information, even from external sources like alt text. Then they manually clean up the data to ensure accuracy.
So they're not just describing what's in the image, but also adding relevant context and details. Like instead of saying a flower, they'd say a red rose, known for its velvety petals and sweet fragrance.
Precisely. They want to move beyond vague descriptions and provide captions with high informational value. They even fine-tune an open-source VLM, Qwen2VL7b, on this data to generate these knowledge-rich captions.
Okay, so they're using GPT-4o to create training data for Qwen2VL7b. That's a clever way to leverage a powerful model to improve a smaller one. What's the final result?
They created a dataset called Hunyuan Recap 100M, which contains 100 million image-text pairs. They found that VLMs pre-trained on this dataset performed significantly better than those trained on alt text or other synthetic captions, especially in perception tasks.
So it's not just about reducing hallucinations, but also about improving the model's ability to understand and interpret visual information. Did they test it on anything specific?
Yeah, they tested it on 15 vision language tasks and saw a performance gain of at least 6.2% compared to other datasets. They also tested it on 20 common cognitive domains like animals, plants, and landmarks, and saw an improvement of at least 6.8%.
That's a pretty solid improvement across the board. What about text-to-image generation? Did they see any benefits there?
Definitely. They fine-tuned a text-to-image model called Hunyuan DT with their dataset and saw a significant reduction in the FED score, which is a measure of image quality and realism. It dropped by 17.1 on a real-world validation benchmark and 13.3 on the EMS-COCO benchmark.
So the images generated were more realistic and aligned better with the text prompts. That's a great outcome. It sounds like this Hunyuan Recap 100M dataset could be a valuable resource for the vision language community.
Absolutely. And they're releasing it publicly to encourage further research in areas like VLM pre-training, text-to-image, and text-to-video generation. It's all about pushing the boundaries of what's possible with multimodal AI.
That's fantastic. It's great to see research that not only improves performance, but also addresses the critical issue of data scarcity in the field. Low hallucination, knowledge-rich synthetic captions. Definitely a step in the right direction.
So this paper introduces NaVAB, which stands for National Values Alignment Benchmark. It's designed to see how well large language models, or LLMs, align with the values of different countries.
That's interesting. I've heard about LLMs having biases, but I didn't realize there was a benchmark to measure value alignment across different nations. What's wrong with existing benchmarks?
Existing benchmarks often use questionnaires, which are static and don't capture the dynamic nature of values across countries. Plus, they don't have enough data to really get a good sense of things. Think about it. Values aren't fixed. They evolve, and they're different from place to place.
Right? Like what's considered acceptable in one country might be totally taboo in another. So how does NaVAB tackle this?
NaVAB uses a value data extraction pipeline to build datasets for value assessment. It also has a conflict reduction mechanism to filter out values that clash, ensuring a high-quality benchmark.
A conflict reduction mechanism. That sounds crucial. Can you break down the data extraction pipeline?
Sure. It's got 3 main steps. First, there's topic modeling to pull out topics from raw news data. Then, value-sensitive topic screening to filter for topics that are actually relevant to values. Finally, value assessment data generation to create statements for evaluation.
So it's all based on news data? Where does that come from?
They collected news from official media sources in China, the US, the UK, France, and Germany. Think CNN, the New York Times, BBC, and similar outlets.
Okay, that makes sense. Official sources should give a good indication of national values. But how do they actually extract the topics from all that news?
They use a process called topic modeling. First, they embed the news using language-specific sentence transformers. This turns the text into numerical vectors. Then they use UMAP, which stands for Uniform Manifold Approximation and Projection, to reduce the dimensionality of those vectors.
Wait, why reduce the dimensionality?
Good question. It's to make sure that news articles with similar themes cluster together. UMAP helps simplify the data while preserving the important relationships. After that, they use HDBScan, or hierarchical density-based spatial clustering of applications with noise, to actually group the news embeddings into topic clusters.
That's a mouthful. So it groups similar news articles together. What about the articles that don't fit neatly into any cluster?
That's where instruction tagging comes in. They use GPT-4 to tag and categorize those outliers, the news articles that HDBScan couldn't classify. It's an iterative process, tagging in batches and then consolidating the tags to create cohesive topics.
So, GPT-4 is like a safety net for the articles that fall through the cracks. Clever. Once they have these clusters, how do they figure out what the topics are actually about?
They create topic representations using a hybrid approach. They combine CTF-IDF, which is class-based term frequency inverse document frequency, with LLMs. CTF-IDF identifies key terms, then keybert and maximal marginal relevance extract diverse keywords, and finally GPT-4 generates topic descriptions based on those keywords.
Okay, so they've got their topics, but not all topics are value sensitive, right? How do they filter those out?
Exactly. That's the value-sensitive topic screening step. They use GPT-4 again, this time with in-context learning, to match documents against predefined topic sets. And to make sure it's accurate, they have humans double-check the selected data.
Human oversight is always a good idea. So after all that filtering, they finally get to generating the value assessment data. How does that work?
First, they extract value statements from the filtered news articles using GPT-4. These are ideological statements, like ethical assertions or policy positions. Then, humans verify that the statements within a nation don't conflict with each other.
That sounds like a lot of work for the humans. What happens if there are conflicting statements?
That's where the conflict reduction method comes in. It's graph-based and uses LLM analysis. They build a knowledge graph where news articles are nodes and value statements are edges. They enhance conflict detection by adding relationships based on semantic similarity, geospatial distance, and social networks.
So it's like connecting the dots between different articles and statements to see if they align. How does the graph help them find conflicts?
They use a pathfinding technique to detect cycles in the graph. Cycles involving conflicting statements can reveal broader inconsistencies. Then they flag and remove the statements that deviate significantly from the dominant stance and repeat the process iteratively.
That's a pretty sophisticated way to resolve conflicts. What's the next step after that?
They classify the statements into quoted statements, which are opinions attributed to specific people or organizations, and official statements, which are direct expressions of views by the media outlet itself. Again, GPT-4 is used for this classification.
Okay, so they're distinguishing between individual opinions and the official stance of the news source. Finally, how do they create the actual evaluation samples?
They generate contrastive samples. For each validated value statement, they use GPT-4 to create a triple structure: a question, the original statement, and a reverse statement. This gives them a way to test whether LLMs align with the original value or its opposite.
So it's like a multiple choice question, where the LLM has to pick the answer that aligns with the correct value. How do they actually evaluate the LLMs?
They ask the LLMs to respond to the question and then use GPT as a judge to determine whether the answer aligns more closely with the original statement or the reverse statement. They also use a multiple choice evaluation method where the LLM selects the statement that better answers the question.
And what's the metric they use to measure alignment?
They calculate the correct rate, which is the proportion of correct responses across all prompts. A higher correct rate means better alignment performance.
So what did they find when they tested different LLMs on NaVAB?
They tested various types of LLMs, including base models, instruct models, MOE models, and closed source models like GPT-4 and Claude 3.5. They found that base models aligned worst, while MOE models generally outperformed the others. Larger models also tended to align better than smaller ones.
Interesting. So size matters when it comes to value alignment. Did they notice any differences between the different countries?
Yes, alignment performance varied slightly across nations. For example, alignment for Germany was generally lower than for other countries. Datasets in English and Chinese tended to have higher alignment scores, possibly due to the pre-training language corpus of the LLMs.
That makes sense. The LLMs are probably trained more on English and Chinese data. What about the difference between quoted statements and official statements?
They found that LLMs aligned similarly with both sets, suggesting a strong connection between individual and official media values within each country.
So people's values tend to align with what the official media is saying. That's not too surprising. Did they do any experiments to see how much the conflict reduction process actually helped?
Yes, they did an ablation study. They found that removing the conflict process decreased the model's correct rate, and that applying DPO, or direct preference optimization, improved alignment performance. DPO is a technique to directly optimize the language model based on human preferences.
So conflict reduction and DPO both contribute to better value alignment. What are some of the limitations of this study?
The dataset is sourced from open media platforms, which may not fully capture a nation's core values. Also, there's limited data availability from certain nations, and pre-trained models for some languages are rare. The evaluation metric also has limitations in multi-round dialogues.
Okay, so there's room for improvement in terms of data sources and evaluation methods. Overall, it sounds like NaVAB is a valuable tool for understanding and improving the value alignment of LLMs across different nations.
Okay, let's dive into this paper on enhancing geometric problem solving with multimodal LLMs. The title is Enhancing the Geometric Problem-Solving Ability of Multimodal LLMs via Symbolic Neural Integration. Sounds pretty technical, right?
Definitely. So what's the core problem they're trying to solve?
Basically, it's about making MLLMs better at geometry. MLLMs have made strides in general reasoning and even some math, but geometry is still a tough nut to crack. It needs precise visual understanding and multi-step logical reasoning based on theorems.
Right, because you need to see the relationships in the diagram and then apply the right theorems in the correct order. What's their approach to tackle this?
They're proposing a system called GeoGen. It automatically generates step-by-step reasoning paths for geometry diagrams. The key is that it uses symbolic reasoning to create a large dataset of high-quality question-answer pairs.
Symbolic reasoning? So like using formal logic and theorems instead of just guessing based on patterns?
Exactly. It's precise and guarantees correctness. Then they train another model, GeoLogic, on this synthetic data. GeoLogic acts as a bridge between natural language and the symbolic system.
A bridge? How does that work?
GeoLogic learns to translate natural language solutions into the formal language that the symbolic solver understands. This allows the symbolic tools to verify the MLLM's outputs, making the reasoning more rigorous and reducing those pesky hallucinations. You know, when the model just makes stuff up.
So it's like having a fact-checker for the MLLM, but one that speaks the language of geometry theorems. Makes sense. What's wrong with how geometry problems are usually solved by AI?
Existing MLLM solvers often rely on supervised fine-tuning, but there's a lack of good training data with detailed reasoning steps. Creating this data is hard. Template-based methods are too rigid, and letting LLMs generate the solutions directly can lead to unreliable results.
So the data is the bottleneck. What about symbolic solvers? They've been around for a while, right?
They have, and they're good at precise reasoning. But they rely on manually crafted rules, which limits their scalability and adaptability. It's hard to create rules for every possible geometric situation.
Okay, so GeoGen is trying to get the best of both worlds. The reasoning power of symbolic systems and the language understanding of LLMs. How does GeoGen actually create this training data?
It's a pipeline with a few key steps. First, it samples random geometric conditions and renders diagrams using OpenCV. Think of it as randomly creating triangles, squares, midpoints, etc.
So it's not just using existing diagrams, it's making its own. That's cool. What's next?
Then the target finder module uses the symbolic system to perform a forward search. It starts with the initial conditions and applies theorems to derive new conclusions. It basically explores all the possible geometric relationships within the diagram.
Like if this is a square, then all sides are equal, and the diagonals bisect each other and so on.
Exactly. It builds a directed graph of all these logical dependencies. Then it selects a target, a conclusion it wants to prove, and traces backward through the graph to find the reasoning path that leads to it.
So it's automatically generating problems and solutions. That's pretty neat. What about turning those formal solutions into natural language?
That's where the LLM comes in. GeoGen uses an external LLM to translate the structured reasoning paths into coherent natural language explanations. It's like having a geometry tutor explain the steps in plain English.
And this is how they create the GeoExpand and GeoSynth datasets, right?
Yep, GeoExpand expands existing datasets with these automatically generated solutions, while GeoSynth creates new diagrams and solutions from scratch. They end up with a ton of data, like 45K solutions in GeoExpand and 62K in GeoSynth.
Okay, so they've got the data. Now how do they use GeoLogic to improve the MLLM's reasoning?
GeoLogic is trained on pairs of formal and natural language solutions. It learns to translate the MLLM's natural language reasoning steps into the formal language that the symbolic solver understands. This allows the symbolic system to verify each step of the MLLM's reasoning.
So during inference, the MLLM proposes a step, GeoLogic translates it, and the symbolic system says yes, that's valid, or no, that's wrong?
Precisely. They even explore a tree-based search algorithm where the MLLM generates multiple candidate reasoning steps and the symbolic system verifies them step by step. This helps reduce errors and hallucinations.
That sounds like a robust system. What were the results of their experiments?
They showed consistent improvements across various MLLMs on geometry benchmarks. The integration of LLMs and symbolic systems led to more reliable and interpretable solutions. Basically, it works.
So what are the key takeaways here?
The main points are: GeoGen, this pipeline, can automatically generate step-by-step solutions for geometry problems. They created GeoExpand and GeoSynth datasets with tons of question-answer pairs. And GeoLogic enables the integration of symbolic systems as verifiers during MLM inference, making the reasoning more reliable.
It sounds like a significant step forward in getting AI to truly understand and solve geometry problems, not just memorize patterns. The symbolic neural integration is a clever way to combine the strengths of both approaches.
All right, let's dive into this paper on geometric problem solving with multimodal large language models, or MLLMs. The paper introduces something called GeoSense, which is a new benchmark for evaluating how well these models can reason about geometry.
So what's the big deal with geometry problem solving? Why is it a good test for AI?
Geometry is tricky because it requires both visual understanding and symbolic reasoning. You need to see the relationships in the diagram and then apply the right formulas and theorems to solve the problem. Humans are good at this because we can identify geometric principles and apply them in context. The authors argue that current benchmarks don't really test both of these skills together in MLLMs.
Okay, so what exactly is GeoSense designed to do differently?
GeoSense is a bilingual benchmark. It supports both English and Chinese that focuses on evaluating MLLM's geometric reasoning abilities through the lens of geometric principles. It has a 5-level hierarchical framework of geometric principles, a data set of 1,789 problems, and a new evaluation strategy. The hierarchy spans plane and solid geometry, covering everything from basic definitions to complex theorems and formulas.
5 levels sounds pretty detailed. Can you give an example of how these principles are organized?
Sure. At the top level, you have broad categories like plane geometry and solid geometry. Then it gets more specific, breaking down into areas like graphical computation and conceptual understanding. Finally, at the lowest level, you have the specific definitions, theorems, and formulas themselves. So it's a very structured way of organizing geometric knowledge.
And what about the dataset? Where do the problems come from?
The problems are sourced from existing benchmarks and the IXL website. The key is that they're intricately annotated with the geometric principles needed to solve them. They use 23 expert annotators to identify 5,556 geometric principles within the diagrams.
That sounds like a lot of work. So how do they actually evaluate the models using GeoSense?
They have two main metrics: geometry principle identification, GPI, and geometry principle application, GPA. GPI measures whether the MLM can identify the correct geometric principles needed for a problem. GPA evaluates whether the model can correctly apply those principles to the specific elements in the diagram. They also use answer accuracy as an overall measure of performance.
So it's not just about getting the right answer, but also about understanding why the answer is correct. That makes sense.
Exactly. The paper highlights that even if a model gets the right answer, it might not be applying the principles correctly. Or it might identify the right principles but fail to apply them in the right way. That's why both GPI and GPA are important.
What were the key findings from their experiments with different MLLMs?
They tested a bunch of open source and closed source models. Gemini 2.0 Pro Flash performed the best overall, but even it struggled with GPA, meaning it had trouble applying the principles correctly in the visual context. The models generally did better with computation tasks than with understanding tasks, and they struggled more with plane geometry than solid geometry.
Why the difference between plane and solid geometry?
Plane geometry involves a larger number of geometric principles, and many of these concepts are easily confused. Think about determining the similarity versus congruence of triangles. It requires careful visual processing and spatial reasoning, which can be challenging for MLLMs.
So what's the takeaway here? What does GeoSense tell us about the current state of MLLMs and geometric reasoning?
The big takeaway is that identifying and applying geometric principles are still major bottlenecks for MLLMs. Even the best models struggle with these aspects, which limits their overall reasoning ability. GeoSense provides a way to pinpoint these weaknesses and guide future research towards more robust and human-like reasoning in AI.
It sounds like GeoSense could be a valuable tool for pushing the boundaries of what these models can do. It's not just about getting the answer, but about truly understanding the geometry.
Precisely. And that's what will ultimately lead to more capable and reliable AI systems. Well, that about wraps it up for today's episode. We really went down the rabbit hole, didn't we?
We certainly did. From ensuring the safety of these powerful language models across their entire life cycle, to helping them truly see and understand the world through vision and language integration, it's been a fascinating journey.
It's amazing to think about how much effort goes into making sure these AIs are not only powerful but also aligned with our values, especially across different cultures. That national values alignment benchmark was eye-opening.
Absolutely. And seeing how researchers are tackling the challenge of hallucinations by creating better training data is crucial for building trust in these systems. Those low hallucination synthetic captions are a game changer.
And who knew geometry could be such a challenge for AI? It's not just about crunching numbers, it's about understanding spatial relationships and applying logical reasoning. That symbolic neural integration approach seems really promising.
Definitely. It's clear that we're moving beyond just pattern recognition and towards a deeper, more human-like understanding. It's exciting to think about what the future holds as these models continue to evolve.
It really is. Thanks for joining us on this deep dive. We hope you found it as insightful as we did. Until next time, keep exploring the world of AI.
And don't forget to let us know what topics you'd like us to explore next. We're always looking for new and exciting areas to delve into. Thanks for listening.